Hey guys, this is Connor Tripp. This is the ECE 461 Challenge 1 demo. This is going to be for the hardware. So right here we have the IDE, and we're going to go ahead and load the code. Alright, and now that the code is loaded, we will disconnect the board so that it's running on only USB power after plugging it back in. Alright, notice the LED that's blinking on the left is simply a diagnostic for the timer A0 that I set. Has nothing to do with the watchdog timer. Alright, and we'll force a reset on the watchdog, and in a minute it should show a green LED showing that the flash has been written successfully. And you saw the red LED light up for a second. That was the watchdog forced. And now we'll wait for the flash write. And there it goes. That's the successful flash write, and that should happen every single minute with a second or two over just to give time for the system to actually do the write. And that should be it. That's the hardware. One more time for the watchdog. And there you go. Alright, that should be it for the hardware. Alright, let's go ahead and look at the code here. At the top we have just some pound defines and includes, as well as a couple globals that will be used in the timer and the interrupt service routine that will be used in main. Starting off with watchdog hold timer, just holds off the timer while we initialize everything. Port init just initializes the ports. We'll go over here and take a look at that. Right here we have the setup for the switch and for the port 1.0 LED, making that LED an output and setting the switch pin GPIO high so that when it's pressed it's grounded, but also making it a input so that it can be looking for that when we're polling, and of course setting the pull-up resistor. Here is just for the RGB LED set on the board, setting all of them to outputs and setting them low for right now. Coming back to here, init timer A, we'll go and look at that. This is just simply using the API to pass in the configuration struct and setting up the timer A to a quarter of a second in up mode, and going ahead and starting that counter right here, as well as registering the interrupt CCR0 so that we can use that to reset the watchdog counter and keep it from triggering a reset. Next we have the timeout reset, or rather we have the watchdog init timer, just passing in the values for that. It's going to be sourced from the A clock and with a clock divider at 32K. This is just going to be like a real-time clock around 32,000 hertz. Set the timeout reset to a hard reset, and finally start the watchdog timer. And then this next part right here simply checks the hard reset register, the status register, and that can be found right here. And source 1 is the watchdog hard reset, and we can look at that in code here in a minute when I go to debug. So this is what would tell the LED to toggle in the timer when the watchdog actually triggers a reset on the board. Moving on, these two long function calls to the API are protecting the bank 0 flash memory space, which is where our code base is, and unprotecting the bank 1, which is what we want to write the 128 kilobytes in. This is all initializing the void pointers to the write regions for each block that we're going to end up writing. And then this is simply writing an array for the data source that we're going to write into the flash. I suppose if I wanted to optimize this, I could have done a mem set instead, but this is the way I chose to do it. Alright, and this is the almighty while. So this starts off checking if the flash program flag is true. So basically what the flash program flag does is it checks the flag, which is set and toggled in the CCR0 timer interrupt. So once a minute has passed, the flag will be triggered true, and then it will go in to write the flash. So int test is just a verification variable that we're going to assume right now that the flash write is going to be successful. And since it's unprotected right now, we're going to perform mass erase on bank 1, and that's going to clear everything. No operation right there, just to set a breakpoint on. And then we're going to call 8 times to the program memory API and write the pattern in, which is A050. Once that's done, the flash program flag will be set back to false, so it's ready to be set true again later on once a minute has passed again. And we're also going to toggle the green LED and set the LED 1 second flag true, so that the timer knows to start counting a second before it toggles that LED back off again. These two are going to these two are just variables that are going to be used to verify with. So right here, these variables are put in 2 for loops. The reason there are 2 right here is because using one large for loop to verify each memory space or each memory address at 32 bits takes too long, and it will trigger a watchdog reset. So we broke these up so that when this one comes back, the timer interrupt flag is ready, and it will go service that ISR, clear the flag, or clear the watchdog counter, and it will come back and verify the other half right after that. And right here, it just checks if test has become 0. If it has, each of these should return 1, and test will be ended with it. So if it ever returns 0, test will be stuck permanently at 0 until the next time it runs through the program. So if test is 0, we know that it has failed one of the verifications. We know that one of the 32-bit integers that we checked didn't match the pattern. And I just have it here setting the timer interrupt disable, so that if there is a failure in verification, the watchdog will trigger a reset. And finally, this is outside of the flash program structure. It will just poll the switch 1 every single time that it goes through. Alright, so let's go ahead and give this a run and check some of the variables as we run through. let's give this a shot. So we're going to go ahead and wait 1 minute, and while I'm waiting for it to hit this breakpoint right here, I'll just say that I could have not used the timer. I could have used software delays like in a for loop right here, but I chose not to, just to optimize. And I believe that if you don't do that, you do get some optimization advice like this inside your advice window. But if I wanted to do that, I could always set a breakpoint on either side of this for loop right here, and look at like a breakpoint like this where it's just simply counting cycles, and count the cycles on either side of it, and that would tell me how many cycles I could calculate out for the clock to make that software delay accurate. Alright, so it's gone ahead and stopped, and we can look in the memory viewer. The flash addresses, as we can see in this document, go from 0 to 3 FFF, and it's split up into 128 kilobytes per bank. So we're just going to use bank 1 because our code is down here, so we want to use the upper half, and we're going to use 0x 20,000 to 3 FFF F. And we can check that right here. And right now it has not been written. And we can go all the way to 3 FFFF. And we see that every little bit has been erased, which makes sense because of this command right here. Now let's go ahead and program it. Alright, and now we can see that 3FFF all the way down has been programmed with our pattern. You can check the top. All the way down has been programmed. So now that we're at this breakpoint, we can check the verify. And once we get down to this line right here, verify should be at 40,000 hex, and that means that it has checked every single value, and if it doesn't toggle a reset, that means every value is good. And let's view our expressions, and there it is, 40,000 hex. And no watchdog timer reset was triggered. So one last thing is we can check the watchdog timer, forcing it on a switch, and that should stop right there. So let's give it a try. And there it is. And we can check the reset control register, check the status, source 1, and there it is. And then once we go through here, it'll reset that status register so that it's ready to look at again and capture that there was a reset on the board. And finally, the interrupt right here is where pretty much all the magic happens. So this LED right here is just a diagnostic LED. It shows every quarter, it'll toggle every quarter second when it comes into the interrupt, just to demonstrate that the watchdog is getting cleared, and to show if there's any jitter. And these two lines right here reset the watchdog counter and clear it so that it doesn't overflow and trigger a reset. This clears the flags for the interrupt. This increments the minute counter, so this is a quarter second timer. So every single time it comes back through, it increments this global external value. And once it hits 240, which is a minute, 240, 60 times 4, you get your quarter of a second minute. Once it hits a minute, it will trigger the flash program flag and reset itself back to 0 to start counting a minute again. And this is another global that main can access, and it will check this flag every time it goes through the while loop to make sure that it hasn't been in a minute yet. And of course, if the flag is high, it has been a minute, so it'll go ahead and program the flash. And then this LED flag right here, it's actually the opposite. Main will set this flag to 1 if it wants to count, if it wants the timer to count a second off for toggling an LED. So once main toggles an LED, it'll set this flag high in software, start counting, counts up to 4, so you get your 4/4 of a second for 1 second, and then the LEDs that we're timing will set back low again. That way we can get those nice second times for the green and red LED for when the flash has been written successfully or when the watchdog resets. And of course, because of the nature of this being a quarter second interrupt, you'll have anywhere between 1 second or 1 second, 1.25 second for those LEDs to be on, because you don't know how far away from the next interrupt call it's going to be when you set your value here in main, right here, say. But anyway, that's pretty much it. Thanks for watching.